Okay, can you see it?
Yep.
Okay, great. We'll get started then. Okay, so this is chapter 5, function minimization with autograd. I'm going to just show my RStudio screen, but you can follow along in the notes too.
Yep.
So the learning objectives, this is covering concepts that we learned in the previous 2 chapters. So those concepts were tensors and function minimization.
Right.
So we're going to be looking at an example, and the example is this Rosenbrock function. It's a function of 2 variables, and it's a popular one to use for testing optimization approaches. So the book said that the function has a minimum at 1, 1, and I think that's the case for the values of a and b that they gave us. But I was looking at some other resources, and it seems like it's more general that the function minimum is at a squared in general. And we can show that too a little bit later if you don't believe me. So the function is shown here, and then a picture below. And I'm assuming they're using these values for a and b, 1 and 5. So here, the really bright white part is the minimum, and that's at 1, 1. You can barely see the x and y labels there, but they're there.
Yeah.
So here's our R code. We're going to start with a equals 1 and b equals 5. And then we define our Rosenbrock function. So we set x1 and x2, and then the function that we'd seen above. And for this case, since a is equal to 1, we expect the minimum of this function to be at 1, 1.
Since you say what? Since
So the minimum of the function in general should be a squared. And since a is 1, then our function, or our minimum, we expect to be at 1, 1.
Okay.
Yeah. Okay, so we're going to look at how we minimize this function using torch. So our goal is we're going to pick some starting point, x1 and x2, and we're going to find the minimum of the Rosenbrock function. And the approach that we'll use is using the function's gradient. So we have this R code set up. So we're going to use torch. We load the library, and we define a learning rate. And for now, we're going to define it as 0.01. And then we're going to have this for loop, so we have to pick some number of iterations, and we're going to use 1,000. And these are both numbers that you can change. Okay, and then x is our starting point. It's a tensor. -1, 1 is just arbitrary. We could set that to really any starting point. And then we're going to set requires grad equals true, because x is the parameter with respect to which we want to compute the function's derivative, or the gradient. Okay, so the steps are, so we're going to do this loop for some number of iterations, and in each iteration, we're going to compute the value of the function at the current value of x, and then we'll compute the gradient at x, so that's the direction of steepest ascent. And then we'll take a step of size our learning rate and the negative direction of the gradient, and then repeat.
Yeah, I have a question.
Yeah.
That mean going to the negative direction of the gradient. So this is something that I was wondering for quite long. What does that mean? Taking to the negative direction of the gradient.
Yeah, so it's like you're standing. If you could look at that picture, you're kind of standing in that space, and you're saying, okay, what direction should I go? And so the gradient's saying, okay, go this direction. That's the direction of the steepest ascent. But since we want to minimize, we're going to go the opposite direction to go in the direction of the steepest descent.
Right. So what you're saying is, when we calculate the gradient tell us to go the steep direction, the up, what do you call to go where?
This direction of steepest ascent, so up the hill. Yep, so it's a vector, it's just a direction. So since we have 2 variables, x1 and x2, we're in that xy plane, or x1, x2 plane. It's saying go that direction. But again, since we're minimizing, we're going to go in the opposite direction.
So Right. So steeped. So when we calculate the gradient, it's calculating the steeped. What do you call it?
Steepest ascent?
The steeped descent. So steeped descent means the way to go up. Is that correct?
Ascent, yeah. Steepest
Ah.
ascent. Yep.
Oh, it's accent. Steeped ascent.
Ascent with an A, and then descent with a D to go
Ah.
down. Yeah.
So if I understand, when we calculate the gradient, it gives us direction of steeped ascent, right?
Mm-hmm.
But we want to minimize, so we go the opposite direction to go descent.
Right. Yep.
Ah, right, right. Because I was wondering for quite long why we always say we go to the negative direction of the gradient, and
Yeah.
yeah,
Yeah, you kind of have to go back to your calculus classes, which has been a
yeah,
few, a few years for me. I don't know about you, but yeah.
yeah. Okay, cool. I really happy, like, to get the point. Because of the example you gave, it's quite understandable. Thank you.
Yeah. Okay. Okay. So we're going to go in that direction, but we have to decide how big of a step to take. So that's our learning
Mm-hmm.
rate, 0.01. Okay, and then we just keep repeating that to try to find at each step. We then look again to see, well, which direction should I go? Okay,
Mm-hmm.
so here's the code, and this is from the book, and we'll kind of walk through it. So we have for I in 1 to number of iterations, which is currently 1,000. Then we have a few print functions here. It's just printing the iteration, the value of the function, and the gradient. So to get the value of the function, we just compute, we have this Rosenbrock function, and we input the value of x at the current iteration. We get the value.
Mm.
And then next, we want to compute the gradient. And remember, we learned in a previous chapter that that's using that backward function.
Mm.
So backward applied to the value. And then previously we set x, when we defined x, the tensor, we said that we wanted requires gradient. And
Mm-hmm.
because we did that, then we can look at this gradient attribute of x.
Mm-hmm.
So that's how we can look at the gradient once we've computed it. Okay, and then down here, we're doing our step. So x, that's our current location. We're going to subtract from that, that's the sub function, the learning rate times the gradient.
Mm-hmm.
And I don't know if you remember from the previous chapter, but this underscore was in chapter 3. It just means update x. If we
Okay.
got
Mm-hmm.
rid of the underscore, then we would just subtract it, but x wouldn't get updated.
Mm.
Okay. Okay, so we're saying with no gradient here because we're updating x, but any calculation that's done on x automatically would get included as part of the gradient calculation. But we don't want this to be part of the gradient calculation, so we have to wrap it with this no gradient function.
Yep. So this is the same also with PyTorch code. You also
Okay.
say no with no gradient, and you zero everything before you go to the next iteration.
Okay. Have you used
So that
PyTorch?
yes, PyTorch,
Oh,
yes.
okay. Okay. Yeah, I haven't.
Mm-hmm.
This is new to me. I've used Keras, but we don't have to do this. Unless it's
Yeah.
done maybe it's done in the background and just hidden from the user. That's possible.
Yeah. Yeah.
So yeah, with no gradient, okay, we're going to subtract off, since we're going in the negative direction of the gradient, we're going to subtract off the gradient times that step. And then also by default, Torch accumulates the gradients, which we don't want, so you have to zero it out each time.
Mm.
Okay, and
Right.
then yeah, so let me run this. I have to go back up and run the code before it actually. So here we're defining, and then we do our setup. Okay, for some reason I can't hit play right now. That's strange. Okay, I should be able to run each line one by one. I don't know what's going on. Okay.
Are you on Mac?
No, I'm on Linux.
Okay.
Okay, so we've defined x, we've defined our Rosenbrock function, learning rate, number of iterations,
Mm-hmm.
loaded torch. Okay, so now we'll do this for loop. I don't know why I can't hit play there. That's weird. Okay, so it's
Mm-hmm.
finished and it's spitting out here the value, the value of the function
Mm.
and the gradient at each. I'm printing at iteration multiples
Yeah.
of 200. Okay, so we get to iteration 1000. The value is this really small number. If I remember right, I think
Is
the minimum
is
of the function is
decreasing?
0.
Okay.
And then
Right.
if we look at x, remember we said that we believe the minimum should be at 1, 1.
Mm-hmm.
So that's pretty close. So if we were to do
Oh.
more iterations, we should get even closer to 1.
Mm-hmm.
In fact, I could
Right.
even do that again. So here's another.
But I think it will start from the beginning, right? To
Well,
need.
I didn't like zero anything out or reset it. So I think it'll just do more. Yeah,
Yeah.
we're getting even closer.
Oh, nice. Okay.
Yeah. So yeah. So anyway, we're close to that minimum value of 1, 1. So any questions on that?
Yeah, sounds good.
Okay. So there was a exercise that they had. It asked what kind of difference does the learning rate make, and then try different
Oh
values
yeah.
of learning rate. Did
Mm-hmm.
you happen to do that?
No,
Okay. So I did it. So it's kind of what you expect. If you use a smaller learning rate, then it's just slower. So I had
slower,
to
yeah.
run a lot more. I had to run a lot more iterations to get to the 1, 1, the
But what
minimum.
about if you use the larger,
Yeah. Well, that was interesting. It actually gave nans.
yeah, it will.
Uh,
So what happened is they have what you call, it will. I forgot this concept, what they call in, using land rate, large. Um, yeah. What is it called? I actually forgot. But they
oh,
have what,
okay. I'm not
yeah,
sure.
they have what they call something, that when you use line rate, which is large, it jump into something. Yeah, let me check.
Okay.
Um, overshooting. Um,
Overshooting. So that
yeah.
makes sense to me if we overshoot, but I don't know why it's giving nans.
Ah,
I can try it here if you like.
it
So
was we have what is called instability. Uh, look at what it says. Let me share with you.
large learning rates can lead to numerical instability. Okay, in training, it can cause issues like nans. Oh, perfect. That's exactly what I was seeing.
Mm-hmm.
Okay.
Yeah. So this is answer from ChatGPT.
Oh, really? Okay. Your your new assistant, which may or may not be right, right?
Yeah, may not be right.
We'll have to
Yeah.
double
Yeah.
check that, but
Something that is obvious, something that is obvious,
right.
yeah.
Okay.
So,
All right. Maybe I don't need to check that.
mhm. So,
Um,
so
yeah, go
what do
ahead.
I mean? Can lead to numerical instability in training. It can cause issue like line value in the gradient or loss, making the training process halt. Okay, prematurely. Okay. So lead to numerical instability in training. It can cause issue like line value in the gradient or loss. So in the calculation of the gradient or loss, it causes none, and making the training, because we have none, it cannot continue, right? Prematurely.
Yeah, I
Okay.
don't fully understand why. I'd have to think about that or look into that
Okay.
more. Because it
Okay.
seems like the gradient calculation would be okay because it doesn't depend on the learning rate. And then you make a step, you take your step that's too big, but you have to think about that.
Mm. Yeah. Okay. One way, like for example, use a large learner rate. So for example, if you are using small learner rate, you can go step, and you can change the rate. But when you are moving, you large, you can overshoot to this place. You can overshoot to this place. You can, not directly going into the, steeped accent going down, but you are shooting to different place also. That's
Mhm.
what they call, I think, is it divergence? So it calls somehow divergence when you are using also large learner rate.
Okay.
Okay,
Okay.
cool.
Yeah. Yeah. So I guess there's one more thing. Um, So I did want to show you if I change A from 1 to 2.
Yeah.
Yeah, so I did restart my R session, so let me
Okay.
rerun code. Okay, so we rerun our for loop. And then get a new value for X. Let me run some more iterations. I think it takes more than 1,000. Okay, so you can see it's getting close to 2 and 4. So remember I'd said that the minimum is at A and A squared, and currently I have A set to 2.
Okay.
So the book didn't mention that, but it seems like a detail that might be important.
Okay. Right. Cool.
Yeah.
So
So anyway, yeah, this was a short chapter.
yeah, what chapter do we have next? The next
Yeah.
chapter.
Should I stop the recording?
Okay. Yeah.